Hello friends, welcome back. In this tutorial we will study about derivations. Suppose there is a grammar G equals to VTPS, where V is a set of variables, T is a set of terminals, P is a set of productions, and S is a start symbol. And there is a production in P, that is A derives alpha. A derives alpha is a production which is in P, where A is a variable, alpha is a string of variables and terminals. Now suppose beta and gamma are the strings of variables and terminals. Then there is a string beta A gamma. Here we have replaced A by alpha. It means we have applied the production rule A derives alpha and get a string beta alpha gamma, right? So we can say beta A gamma directly derives beta alpha gamma. It can be shown as like this. It can be shown as beta A gamma derives beta alpha gamma, right? We relate two strings by this symbol, right? When second string is obtained from first by only one application of some production. Now suppose alpha 1 derives alpha 2 and alpha 2 derives alpha 3, alpha 3 derives alpha 4, and so on up to alpha n, where alpha 1, alpha 2, alpha 3 up to alpha n are the strings of variables and terminals in G. So it can be shown as like this, right? It indicates that alpha n is derived from alpha 1 in unspecified number of steps, including 0 number of steps. So for each string alpha, this is also true, right? If alpha derives beta in n number of steps, then we can specify it as like this, right? We can use this symbol for this symbol, right? And we can use this symbol for this symbol if it is clear that grammar G is involved, right? If it is already known that grammar G is involved in the derivation, then from this symbol and from this symbol we can remove this G, right? It shows that in derivation grammar G is involved. Now see, if alpha derives beta in exactly n number of steps, then we can specify it as like this, right? Let G is a context-free grammar. Then its language LG will be the set of all strings of terminals which are obtained by applying the production rules in different order, starting from start symbol S. So LG, the language whose grammar is G, is the set of all strings of terminals W. W is a string of terminals which can be derived from start symbol S. Now consider this language, which is a set of strings of the form a raised to power n, b raised to power n, where n is greater than or equal to 1. It means this language is the set of all strings of a and b in which a's are followed by same number of b, like AB, AABB, AAA, BBB, and so on. Let G be the grammar of this language L. G equals to VTPS, where V is a set of variables and this set has only one variable S. T is the set of terminals and it has only two terminals A and B, and P is a set of productions, right? Here there are two productions. One is S can derive AB and other is S can derive A as B, right? Now, so G is the grammar of language L. So those strings which are present in language L should be derived from start symbol S by using different production rules. Now look at here. This string AB is present in language L, so it should be derived from start symbol S, right? So it is the derivation of a string AB. Whenever we start derivation, we start from start symbol S. So we have started from start symbol S, and there is a production S derives AB. So here we have replaced S by AB, right? So in this way, this string has been derived from start symbol S. Now this language has a string AABB. So this string must be derived from start symbol S. So again, it is the derivation of AABB. Here S is replaced by A as B because there is a production S derives A as B. So here we have applied this production S derives A as B. So we have replaced S by A as B. Now this S is replaced by AB because there is a production S derives AB. So when we applied this production, what we get? AABB. So this string has been derived from start symbol S, right? Now see this string. This is also present in the language L, right? So this string should also be derived from start symbol S, right? So here this is the derivation of the string AAABBB, which starts from the start symbol, right? here we have applied the production as derives ASP. So S is replaced by ASP. Now again we have applied the production as derives ASB. So this S is replaced by ASB. Now here we have applied the production as derives AB. So this S has been replaced by AB. So in this way we had derived this string from start symbol S by applying the production rules of P. Now consider this language L. Which is a set of strings of the form W, C, W, R, where W is a string of terminals A and B, C is a terminal, and WR is a reverse string of W. Now let its grammar be G. G equals to VTPS, right? So here T represents the set of terminals, right? So this set will have three terminals A, B and C, because all strings in the language L will be formed of only three terminals A, B and C. V is a set of variables which has only one variable S, which is the start symbol S, and it has following productions, right? P is a set of productions. So in P there are these following productions. S derives A, S, A, right? S can also derives B, S, B, and S can also derives C. Now look at again, right? Here W is a string of A and B, C is a terminal, and WR is a reverse of W, right? It means C should be at the mid of the string and substring which is at the right of the C should be the reverse of the substring which is at the left of C. So let us derive few strings by using the production rules of this grammar G of language L, right? We start derivation from S. So here we have applied the production rule A, S derives. Here we have used the production rule S derives A, S, A. So here we have replaced the S by A, S, A. Now again we have applied another production rule S derives B, S, B. So this S is replaced by B, S, B. Now here we have applied the production rule S derives C. So S is replaced by C. So we have got this string of terminals A, B, C, B, A, right? So this string of terminal will be present in the set L, right? Now see another derivation, right? Let us see the derivation of this string, right? Now see this string is of the form WCWR, right? This string which is at the right of C is the reverse of the substring which is at the left of C. Here also the string which we have derived, in this also the substring which is at the right of C is the reverse of the substring which is at the left of C. Now let us see the derivation of this string. We starts from S, start symbol S. Here we have applied the production rule. S derives BSP, so S is replaced by BSP. Now here we have applied the production rule. S derives ASA, so S is replaced by ASA. Now here we have applied the production rule. S derives C, so S is replaced by C. So in this way we have derived this string BACAB from start symbol S by using production rules. Now let us see this grammar G. It has only one variable S, which is the start symbol. It has following productions. S derives BS, where this small b is a terminal. It has only one terminal, B. S derives empty string, right? Now let us see what types of strings can be derived from this grammar G. We have to see what type of strings can be derived from this grammar G. It means we have to find the language whose grammar is G. We have to find the language of this grammar G, right? Now we always starts derivation from S. Here we have applied a production rule. S derives BS, so S is replaced by BS. So I have again applied this production rule. S derives BS, so S is again replaced by BS. Here I have applied the production rules. S derives empty string, so what I got? BP. This is a string of terminals, right? So language of this grammar will have this string BP. Here there is another derivation. Here we have as we should start from S. So I have started from S. I have applied the production rule. S derives empty, right? So S is replaced by empty. So empty string should also be present in the language of grammar G. Now let us see another derivation. Let us derive another string of terminals. Starts from S, right? Here I applied a production rule. S derives BS, right? Here I have applied the production rule. S derives empty string, so S is replaced by empty. So what I got? B. So B will also be in the language of this grammar G. Let LG be the language of this grammar G. So it will have such type of strings: empty string, B, BB. The way we have derived BB, we can also derive BBB, right? We can also derive BBBB and so on. So these all strings will be present in the language of grammar G. Now see here this empty, right? It is a special symbol, right? It is not a variable because there is no production of this form. Empty derives alpha, so it is not a variable. and it is not a terminal also, because it vanishes from the string. If there is a string empty AB empty, then it would be equal to AB. Now if there is a production A derives empty, and we replace A by empty in some string alpha A beta, then it means we have deleted A, because when we apply this production rule, A will be replaced by empty, and empty vanishes from the string. So what will we get? We get alpha beta. A will disappear from the string, as happened here. Here I applied the production as derives empty. So what I have done here? Here I have deleted S, right? So what I have got? B. Thank you very much.